All right. So last week we talked about vectors. And the first thing we need to talk about is that we need to differentiate them from scalars. So a scalar, as you might recall, has magnitude only. And a vector has both magnitude and direction. This can give us all sorts of applications in, for example, physics. And we talked about some examples last week where, for example, you had distance, whereas the vector equivalent was displacement. You had scalars such as speed, whereas the vector equivalent was velocity. And you could keep listing. You could list, for example, acceleration, force, and so on. But the key point we needed to sort of point out was that a vector must always have a magnitude and direction. It's never just a magnitude. But the scalar is just a magnitude only. And so we talk about how we could sort of represent these vectors. And there are a few different options. So in terms of representation of a vector, we note that it has two things that you need to represent. As we said earlier, there's the magnitude is number one, and number two is the direction. Now we can represent vectors algebraically. That's one option. And we'll probably look at that, today and in the coming weeks. But graphically, which is what we mostly explored last week.
Hello.
Hi, Tiffany.
Hi.
Yep. We're just quickly revising what we did last week. Did you get a chance to look at the link?
Yes.
All right.
Yes, I did.
So, good. Did it make sense while you're looking at it?
Yeah.
Good. All right. Well, we're quickly in the process of quickly revising that. And once we're done, we'll, move on. So graphically, we could represent a vector as what we might call a directed line segment. So that's basically just like a line segment, which means it's got a start. Let's call this A. And then, it'll have an end, which we'll call B. But unlike a line segment, you have an arrow. So in other words, you can think of it as an arrow. And this arrow is a graphical representation of your vector, where the length of the arrow, which can be represented by this, representing the absolute sign, is the magnitude of vector AB. And I guess the arrow itself, the arrow point, represents the direction of the vector. Now remember, who's having the, okay. Yes, you might need to turn the volume down a bit, Tiffany, on your speaker. All right. So that's the directed line segment. Now, if we have, remember, if we have a point A, and this is the origin, then from O to A, this is a vector. So OA is the vector that originates from O, sorry, and terminates at A. But because it originates at O, which is the origin, the vector OA has a special designation, which we can also say is the position vector of A. which basically means position vector basically just says, if we start at the origin and which direction do we need to go? Which vector, I suppose, which direction and distance do we need to go to get to A? So therefore, because A is this point here and O is this point here, then pretty much by definition, anything that starts at O and goes to some point, let's say B, will be the position point, a position vector of B. And in terms of notation, we could write it as OA. Normally, we don't just write capital A because capital O and capital A represents points, but we could write it as, you know, just A, but we want to designate it as a vector, and that could be all sorts of situations like bolding or underlining it with a tilde or putting a cap on it. But those are all sorts of examples like that. More generally, if you're not at O and you're at A and you want to go to B, wherever that is, then this is the vector AB. Now, because I don't want to use the letter A or B, because of the fact that they would generally represent, you know, the position vector A and the position vector B, I will just say we can still give it a letter. I'll call it C here. So it could be any of the other things we talked about earlier. Okay. And we can call that C. And that's just basically a short way so that we won't have to write out A, B all the time. And that's basically your vector notation. But also note that if you've got AB, the length of AB from A to B must be the length of, well, starting at B and going to A. But the direction is obviously different. So we've also noted that for any vector that goes from A to B, it's the negative of the other way around. You're basically just going, you're just reversing it. You're just going the other way. Does that make sense? All right.
Yep.
Is everyone happy with all of that?
Yep.
All right. So that's pretty much what we mostly did. We did a bit of addition. Now, I know some of you were a little bit sort of not so happy with that. So let me go through that again a bit more, you know, hopefully both revising, but hopefully giving you a bit more appreciation of it. And we'll move on to, you know, a bit more on subtraction and other things. So let me use different colors this time. So blue will be vector A, otherwise the position vector OA. And let's say point B is somewhere here. And so let me use green now. And so green will be position vector B. So we'll just write it down on the right. At this point, we've got A, and we have B. And A is just OA, which is position vector of A, and B is position vector of B, which is vector OB. Now, last time when we talked about addition of vectors, I know, Janelle, you weren't here last week, but do you remember the steps for additional vectors? Did you get that far?
I didn't really remember.
Okay, and you said you only went through half of it, so this was more towards the end. So, Tiffany, are you joining us now? Have you sorted out the issues? Nope, she's still joining and exiting. All right, so Paris, do you remember the vectors? Do you remember how to add them graphically?
Isn't it just A plus B?
It is, and how do we do that? How do we work it out?
Oh, you draw a triangle out of it.
Pretty much. So your first step is, if we're trying to work out A plus B, then your first step is to draw out A. From some point. E.g. origin. And so A will go somewhere, right? And then after that, you draw out B. And importantly, from where A ended. In other words, you draw from the end of the arrow. And if, there are more vectors to add, you repeat step 2. You basically draw one more arrow, and then you finish at some place, you add the next arrow, you finish at some place, you add the next arrow, and so on until you've added everything. And the sum.
Does it matter which arrow you add it to?
It doesn't matter the order in which you add it, but you always draw from the very end of where you are at the moment.
Okay.
So the sum, and we can show you that in a moment if you like. We'll start with 2 and we can do 3, but the order doesn't matter as long as you do it properly. So the sum is the result arrow from the start to the end. So let's just do 2 for the moment. So in our example here, let's me pick a point. It could be anywhere. So I'm going to pick that as my starting point. And I'm going to do A plus B, which means if I do A first, I'm going to draw A. In my example, A looked something approximately like this. Remember, a vector has magnitude and direction, which is represented in your arrow by length and direction. So as long as that's the same length as that, which it's probably not exactly, but is intended to be, use a ruler, in your life, in your test. And then your direction, which is intended for those to be parallel, is meant to be the same direction. All right? So I've started here, I've drawn A, and I've ended at this point. In other words, I've done step 1. The next thing I need to do is add my next one, which if I'm doing A plus B, I need to draw B, which looks like this. So I need to start here and draw vector B, which more or less looks something like this. And if I'm only drawing 2 arrows, there's no step 3 because I'm only doing A plus B. So the sum is from the start, which is here, to the end, which is here. And so, if you like, A plus B is the yellow arrow. Does that make sense? So this long arrow here, in this case, the long arrow, it could be shorter. But in this particular case, with this example of A and this example of B, we end up at this sort of length, which is A plus B in my example here. So this is doing it as A plus B. But as I was mentioning before, the order doesn't really matter. So let me do B plus A. So if I start here and I draw B, something like that. And so remember, I've started here and I've ended here at this point in time, and this is the end of step 1. I'm going to add A from here, which means I need to draw a vector kind of like A, like this. So it's parallel and the same length. That's the idea. And therefore, I've started here. I've ended here. After going through B, then A, I've ended here. So from start to end, I draw a new arrow. And this vector here represents, well, B plus A, which I suppose is A plus B. If you compare these two arrows, can you see that ignoring any sort of, human error when we drew it, it's going to be the same length and the same direction?
Yeah.
Janelle, Tiffany, can you all see that?
Yes.
Yeah.
In fact, we can also prove it on this diagram. See, this is A, right? And now let's do A plus B. So if I do A plus B, I'm going to sort of get this sort of thing to about here. And remember, this green arrow is still B. Now, it's still the position of vector of B. Point B is here. This is not point B, but the vector doesn't care about, remember, vector doesn't matter where it is. It only cares about the length, and it is the same length, or should be, and the direction is the same. So therefore, that vector, the green vector here, is the same as that green vector there. Different place, doesn't matter. Same length, same direction is all that matters. So that is vector B, which means that if I go from the start to the end, that is A plus B. Having said that, if I did B and added A, now, okay, my drawing is not perfect, clearly, but remember, these two are meant to be in the same direction and the same length, right? And these two are meant to be the same direction and the same length, right? Now, if you've got these two being the same length and same direction, what can you tell me about these two lines, if we treat them as lines? They're the same length, and if they're the same direction, then they are?
The same.
Parallel.
They're parallel. And these two are the same length and also
Parallel.
parallel, which means this is a parallelogram.
Parallelogram.
So another way you can think about it is if you were to draw out all four sides of this parallelogram represented by vector A and vector A and vector B and vector B, A plus B is just this diagonal here. Or, A plus B is the diagonal. The length of the diagonal is represented by the magnitude of vector A plus B. But yeah, that's the idea. Does that make sense?
Yep.
Yes.
All right, so now let's just also get used to a concept here on the next page. So we'll still focus on A plus B. So we'll do 2. We can move on to more than 2 in a moment, but let's just do that. So let's call this A. And let's call this B. So sort of similar to what we had before. And so applying what we just said, we're just saying, therefore, that if we're trying to work out A plus B, you draw A, you draw B, now this is A plus B, like we said earlier. So you start from here, you end at here. You draw A, you end at the tip of A. From there, you draw B, and you end at the tip of B. So the start of A to the tip of B is your A plus B, and which we'll call C. Now, from earlier, you can probably see that, you know, C is A plus B, which is equivalent to B plus A. That's probably fairly obvious from what we drew earlier with the parallelogram. But you can hopefully now, let's instead of thinking of this as A plus B, think of this as C. Then if C equals A plus B, then what we're really saying is other ways we could interpret this sort of triangle, if you like, is C minus A must equal B, or C minus B must equal A. So if you think vectors kind of work like numbers, then if this is true, then these two must also be true, right? Does that make sense?
Yeah.
So therefore, we now want to sort of talk about subtraction of vectors. Do you guys remember how to subtract vectors? We talked about this very briefly last week. We did briefly mention it, but I think it's sort of worth revisiting if you aren't all clear on it. How do we subtract vectors?
I can't remember.
Right. So if you're trying to subtract vectors, remember, think about this. Think about like a number, right? If you have 5 minus 2, we all know the answer. What's the answer?
3.
Right. Now, let's say you don't know how to subtract, but you know someone who knows how to add. How would you tell them to work out this, you know, sort of this question? If they don't know the answer is 3, but they know how to add numbers, they just don't know how to subtract. How do you get them to 3?
2 plus something equals to 5.
Well, that's one way. That's if you're reversing it, that's true. But let's say, you know, 5 plus what would get you 3?
Minus 2.
Exactly. So in other words, instead of thinking of it as subtraction, which it is, think of it as adding the negative vector. So, for example, if we're doing C minus A, think of it as C plus, which you know how to do, negative A. Now, do you guys remember how to take the negative of a vector?
No.
Oh, but we mentioned it literally today as well.
Yeah.
It's just the same vector, but in the opposite direction.
Oh, okay. I see.
Right? I know we briefly mentioned it last week, but here we said it again. Although, to be fair to you, Tiffany, you were kind of dropping in and out during this period of time. So to get the negative of a vector, you literally just take that same vector, but you swap the arrow. So instead of putting the arrowhead there, you put it over here. So what we're really saying then is if we're doing C minus A, then basically if A is sort of the blue, then negative a is, so if a was like that, then negative a, which I will represent using red for the moment, will literally just be the same line. I'll keep it the same length, hopefully. So that will be negative a. Does that make sense?
Yep.
So it's the same thing, but just the other way. So if we're doing c minus a, that really means we're going to take c, which is roughly this one. So treat it as an addition.
So it'll be B.
Oh, well, it should be, but we're just going to show you that. So this is c, which is a plus b after all. And then we're going to subtract a. So it's going to look something like this. So this is your negative a, which you're adding. So we're doing it like an addition. And then you'll get, I guess, this sort of green vector left. Now, I didn't draw it very well, I suppose, but can you see that it would basically give you b?
Yes.
Yeah. And so in other words, if you draw them out, c minus a will give you b, and c minus b will give you a. If you like, again, maybe think about the parallelogram. If I drew in the sort of negative a on this diagram, the negative a would kind of look like this, but now it's a negative. So go this way. So you would, if you start here and go to c, and then minus a, that means here, and that gives you this arrow, which of course is parallel to that because these blue ones are parallel. Does that make sense?
Yeah.
And if we're doing c minus b, then I guess instead of drawing a new arrow, I've just got c, and minus b just means I'm going this way instead, and that gives me a as the result.
So like no squares, no nothing. It's just that plus that.
Yeah, well, you can make them squares if they're right angles, but yeah, essentially, just think about it as sort of traveling around. So c minus b gives you a.
Okay, cool. Very cool.
So therefore, basically, what you sort of expect does still work out, and I'm showing you that through the diagrams as well.
Mm.
Now, you generally won't be using much more than 2 vectors in the questions you get, but I just thought since it was kind of raised, if you've got something like a plus b plus c equals d, just note that the order does not matter. And we'll show you that in a moment. So for example, whether you do a plus b plus c, or a plus c plus b, or, like b plus, whatever way you switch the order, as long as you essentially get a plus b plus c, all of this are all equivalent. And for subtraction, you just treat it as adding a negative, which means you just flip it around. So let's just pick some examples for a, b, and c, and just do 3 examples and we're done with this. So let's say a looks like that. And let's say b looks like, let's just keep it simple and go down. And let's say c looks like this. That means your a plus b plus c is that.
But that's so weird because it's shorter.
Yeah, they can cancel each other out, remember? So in the example I gave earlier, indeed, here, a plus b is longer, but there's no guarantee that your sum has a longer length, right? A more extreme example, like imagine if you're adding, if this is a, and this is b,
Oh,
directly
so the
backwards.
A was negative?
Sorry?
So the a was negative.
Not really. There's a direction. So basically, there's no guarantee. Like think of it like a 2D sort of problem. Although vectors aren't really just in 2D, we will go on to 3D later on. But basically, think about this as sort of walking around, right? There's no, just because you walk further doesn't mean you're further away from where you're starting from.
Okay. Yeah.
Right? So that's the difference between a scalar and a vector, right? So a scalar doesn't care about the direction. So if you keep walking, your distance will go up, but your displacement, which is a vector, cares about the distance from the starting point. So you might have taken a long kind of way to get here, but that doesn't mean that just because you've walked further doesn't mean, you're actually further from your starting point. Yeah.
Yeah. Okay.
And that's part of the reason why I gave this example here and now, to do two things at once, show you adding up more than two things, as well as, try and dispel any misconceptions you might have about that it must be longer. It doesn't have to be longer. Yeah.
Okay.
All right. So now let's do A plus C plus B using, the first one as a guidance. So if we're picking this is A, then C is now, I haven't really made it clear which one is steeper, have I? But let's give it a go though. So A looks something like this. C looked kind of something like that. Something like that. And your B, which I did not label earlier, looks something like this. And can you see, although the diagram looks very different, can you see that the last one looks essentially the same?
Yep, we get it.
All right, so I take it that you don't need the third example?
Nope.
All right. Good. So therefore, that is addition of vectors. Now, did you both get the chance to do the homework as well? Tiffany, did you get the chance to do the homework?
Yep.
All right.
Did that.
No problem. Okay then, so now let's talk about how to change the length of a vector. So remember, a vector has magnitude and direction. And if we're changing the length, what are we changing?
Magnitude.
Right. So, graphically, this is represented by the length, and this is represented by the arrow direction. And so we are basically changing the magnitude. Now, how do you kind of make an arrow longer? Like, how do you think you would do that? So you don't want to change the direction at all. You don't want to change the direction at all, but you just want to change the length of this.
You keep drawing.
Right. So I guess let's think about it graphically. You're not wrong about that. So let's call this A. And you're saying that basically you want to sort of extend this, right? Now, we could make it longer or we could make it shorter. Let's just stick with longer for the moment. But we want to kind of grow it, using your words, we want to kind of grow it, right? In the same direction, right? So
Yes.
Imagine I want it to be twice as long as before.
You add another one on top of it.
Add another what, to be clear?
Arrow.
Which arrow, specifically?
A. Add
Right.
another A on top of it.
Exactly. You could add another A. So therefore, if this one is A and this one is A, then that would be 2A, right?
Oh.
I mean, using a vector addition, if you're saying you're drawing another arrow, then, you're adding, first arrow is an A, the second arrow is another A. So that would just be, well, A plus A, which is 2A, right?
Yep. Makes sense.
And if you want to go further, you can have 3A, 4A, and so on, right?
Yep.
Now, what if I want to be like somewhere here?
A fraction.
Right. It's 1 and a bit A.
Mm.
And this is obviously sort of half of A. So you can probably see where we're going with this. So to change the length of a vector, you simply multiply that vector by a scalar, by a number, basically. So, in other words, Ka is, you know, a vector with same direction as A, but magnitude K times the magnitude of A. So of course, if K is bigger than 1, then of course you're going to get, you know, longer. If K is between 0 and 1, then it'll be shorter. If K equals 0, then you have no more vector, no vector. So that's a sort of a more special case. And of course, if K is negative, then you have switched the direction. Which means technically you've not just changed the length of the vector, you've also changed the direction. So you would treat the negative part separately. So multiply by a number to change the length. And as we talked about before, if you make it negative, then you'll switch the direction. Happy with that?
Cool. This is surprisingly easy compared to like what we did like last time.
Well, you mean last time as in the trig?
Mm.
Well, to be fair, I kind of, you know, proved everything, whereas you could more or less just remember the results. Yeah. And, you know, vectors is a whole new topic, whereas trig is kind of, you've all done all the basic trig. So, you know, I went a bit more in detail with the trig, whereas vectors, you know, you're just starting. So this is purely definitely all the introduction stuff.
Oh,
so,
no.
You know, and it won't get too hard, but yeah, at least not for the things we're doing. But yeah, it is, it's good that you're finding it easy because, well, bluntly, you should. Yeah. If you're finding this difficult, then it would be a little bit worrying. All right. Everyone happy with everything we're doing so far?
Yep.
Yeah.
All right. So now we've been sort of focusing on vectors graphically. Now we're going to start talking about, you know, vectors algebraically. And you need to know both. But I kind of focus on the graphical one because I didn't want you to just sort of be lost in the sort of, you know, in the algebra and not have any idea of what you're doing. So I'm going to sort of tie back into the graphical sort of every now and then, but we're trying to now focus more on the algebra part now. So let me imagine I have a point sort of A. And let's just say that this point is 3, 4. And you guys, because of, you know, all the things we've talked about last week and this week, recognize that, you know, this is O and this is OA. And so we've got vector OA, right? Which has a particular magnitude and a particular direction, right? All of which we could work out. Does that make sense?
Yes.
All right. In fact, I'll make it a bit easier. So if we call A11, just be clear, what is the magnitude of OA?
1.
Not 1.
The magnitude. Oh. It's. Oh.
Oh. It's root 2.
Right. Because remember, excuse me, that means this distance is 1, right? And this distance is 1, right? So basically use Pythagoras to work out that, well, vector OA is actually root 2 distances units long. Okay. So now, what is the sort of, if we're being sort of numerical about this, what is the sort of direction of OA?
Northeast.
All right, so let's talk about it as 45 degrees to the horizontal. So let's kind of, sooner or later we'll need to start using degrees here. So that's the sort of idea, right? So OA is a vector of length root 2 at an angle. If you think about it as north, south, east, west, then it's northeast. If we're thinking about it in terms of degrees, it's 45 degrees to the horizontal in the anti-clockwise direction, right? So that's sort of, we went from the graphical and we kind of nailed down the magnitude and the direction. And now we want to talk about how to represent it in algebra. So we can represent it as, basically, we can say it's 1 unit across and 1 up. Like, that's how we sort of think about it, right? Think about how you kind of get to point A. We're saying it's 1 across and 1 up. So that's what the X and Y coordinates are, right?
Mm-hmm.
So we could write this. So, 1 unit across, we call this red thing, 1 unit across, a base unit vector. And we normally give it the letter I. So it's 1I and also 1J. So it's therefore 1I and 1J. Where I is defined to be the base unit vector in the X direction. And this is defined to be the base unit vector, basically of length 1 in the Y direction. Now, because, you kind of go to the right and then up, we're saying it's 1I plus 1J, where I and J are vectors. Does that make sense?
Yeah.
Now, if we had a different point, for example, if I had a point B over here, and let's just call it, 7, well, I have to keep it to scale, so 7.5, 7 and then half up, then can you see that, as a separate example, so OB, you would just think of it as 7 across, so that would be 7I plus, in this case, half J. So basically, instead of talking about, we're just basically taking the X coordinate and multiplying it by I, which means how much across, and then taking the sort of, the Y coordinate and multiplying by the J, right? Kind of like our coordinate system, except with vectors, right? Happy with that?
Yep, makes sense.
So now, because we always do that, then OA, we said is 1I plus 1J. And we said that OB, in my example there, was 7I plus half J. Now, because I and J never change, we also write vectors as like that.
Oh.
So this kind of is like this is all just, this is not hard, but it is new for you guys most likely. So just like when you first did coordinates, you had to get used to the fact that, what does 3, 4 mean? Well, this is the X coordinate and this is the Y coordinate and this is how much you go to the left, right, and this is how much you go up, down, all that kind of thing. We're doing the same thing with vectors. So it's not hard, but it is probably new to you. So vectors, OA, is at the point 1, 1, which means it's 1I, 1 across, and 1 up. So that means, we're going 1I and 1J. This is 7I and half a J. Does that make sense?
Yes.
All right. And then, of course, let's say I made up a new point, OC. So let's say C was at the point, 3, -4, or -5. then hopefully you understand that's 3i plus negative 5j, which means therefore that it's going to be 3, negative 5. And it really isn't that much different when you think about it, because really what that basically means then is that you're really just taking the x coordinate and the y coordinate, and you're pretty much just putting the x coordinate here and the y coordinate here. Does that make sense?
Yeah, it's like rewriting it.
Yeah. But having said that, well, that is basically true as far as you're concerned in sort of, you know, working this out. I want to stress, are these points? Are we representing points?
No.
No, we are representing vectors. So, you know, that I suppose is the difference. So, of course, I'm starting at 0, O, the origin the whole time. But one thing to remember here, these are representing vectors. The points, of course, can be sort of linked in if you're starting from O as a position vector, but this sort of notation here itself is referring to a vector. Okay.
Cool.
So sort of another notation, which hopefully you probably won't be tested too much on, but you know, we need to talk about it. So in other words, that means since I is kind of going across, that means I can be written as like this, and J can be written like this. One up.
Oh, yeah.
And then what we will say is that the set of vectors I, J, which represents this, I'm just replacing them with that, is the standard basis for the 2D XY coordinate system. So this new sort of terminology I've kind of used here is something we kind of need to explain, because you might get questions that ask you for it. Basically, standard basis is just a fancy word to, you know, there are going to be more and more fancy words in this topic that we will need to start sort of explaining, and you will need to memorize. It's a new topic with new you know, sort of terminology, but basis just refers to the fact that these, basically with these, you can kind of describe any point on the XY coordinate system. So that's just in the X direction and nothing else. That's in the Y direction and nothing else. And you know, this is length 1 and this is length 1, and they're at right angles to each other. So for you to be the standard basis, your vectors need to be length 1 individually. They need to all have one component only. So that's X and the other is 0. This is Y and the other is 0. And that's 1, 1. And that they're at right angles to each other. That is what makes a standard basis.
Okay.
Which is all a really fancy kind of way to just say, you know, the very basic thing, like if you want to talk about how you get to a particular point, you just want to know how many units across and how many units up or down. That's the short version, right? There are other ways to think about it. You can talk about how many 3 units across, right? Like you can have, you know, instead of this being 1, if you change this to 2, you know, all your scalar numbers would change, but that kind of sort of makes it a little bit more annoying, right? Instead of thinking of every single unit across, you think of it as every double unit across or every 5 units across. So those would still be vectors and they will still form a basis, but they wouldn't be the standard basis. So I'll reiterate again. For the standard basis, you need each vector to be length 1. So I is length 1 because it's just going across 1. J is length 1 because it's going up 1. You need them each individually to have one direction only. So that's 1 and nothing else. That's 0 and that's 1. And that they are at right angles. That will form your standard basis.
Okay, so the standard basis just described that.
Yep.
Okay.
Now, I know we've gone through this, but let's just now talk about the magnitude of a vector. So now let's sort of be more formal about it. So if you have a vector, which is 2, 3, say, that means it's 2i plus 3j, right? So if your vector is 2, 3, it means it's 2i plus 3j, which kind of, if you remember, I is your base, your standard base unit vector across in the x direction, and your j is your base unit vector in the y direction, then that basically means that you're going to get a vector which more or less looks a little bit like this. So remember, this is your 2i, because you're 2 units across, and that's your 3j, which is your 3 units up. And because you're doing 2i plus 3j and you're adding them together, remember you're starting from here and you're ending there. So graphically, that means your 2, 3 vector is this yellow vector. So this vector of 2, 3 means 2i plus 3j, and that's your 2i, and that's your 3j, and that is therefore your vector in total. Now, how do I work out the magnitude of this vector? Can you see graphically how that would be accomplished?
Pythagoras?
Right. This would be just accomplished through Pythagoras. So essentially what that means, it's going to be 2 squared plus 3 squared square root, which shouldn't give you any trouble. It should be square root of 13. And so in general then, if some vector v is composed of v1 and v2, where v1 and v2 are numbers instead of vectors, that means it's going to be v1 I plus v2 j, which means it's going to look whatever v, change the 2 and 3 to vi and v1 and v2, but then the magnitude of the vector is literally, it is just Pythagoras graphically, which then means it's essentially going to be v1 squared plus v2 squared and then square root. And so hopefully, Paris, this clarifies what you were saying last week about, how you thought 2 plus 3 equals 5. And you can see that because it's a vector, what you care about is actually this length here for the magnitude. So you really need to use sort of the Pythagorean theorem here.
Yep.
Good. Any questions with that? And I'll stress
No.
again. Yeah, was there a question? Yeah.
No, I was just saying I have none.
Okay. So I'll stress again, note a unit vector. Do you know what unit means? Do you guys know what unit means?
No.
No, it just means one. So a unit vector is therefore any vector with a length of 1. And so if we go back and talk about I and j, we said that I was the base unit vector in X. That unit just means it has a length of 1. That unit here just means j has a length of 1. It's part of the definition of what it is. Base just means it's in that direction, so you can see that I is in the X direction only, and base in Y just means it's in the Y direction only. And it's a vector. That's why, as I said earlier, these are the base unit vectors. They're that base because it's only in the X direction. It's not sort of slanted. This is vertical only. There's no sort of slant. And so that's why they're the base vectors, and the unit vectors, They're not only are they base vectors, but they're unit vectors because they are length 1.
And they're 1 because you have to times it by that number.
Well, you don't have to. I mean, in the sense that if I was not the base unit vector, but if I just called it some other letter like M, then if that was 2, I just multiply half. You know what I mean?
Oh, I see that.
So that's why we do need to add the word unit. And it is defined that way. So be very careful when you use, the reason I didn't choose to keep with the letter I and I said M is because if you start using I and J and K without sort of defining them, they're usually defined to be the base unit vector. So be very careful when you're starting to use these sort of letters. They're, you know, without further information, you assume them to be meaning the base unit vector.
So does it matter what letter it is, or does it have to be I and J?
Well, usually you know, just like I guess it doesn't really matter if you have an equation in X and Y, that's usually what you work with. So, you know, if you're trying to stick with like, you know, what everyone does and what your textbook does, then yeah, you would assume I is the base of the first one and J is the next one. And if you go to 3D, then K is your third one and so on. Yeah.
All right.
Yeah. All right. Make sense?
Yes.
All right. So now again, our focus is on the algebra. So now let's do vector addition, but this time think about it algebraically. Now, I'm not saying this is a better way to go necessarily. Sometimes you will have, you know, sometimes there are ways where you might think the other way is better, but let's now think of it in an algebraic addition of vectors. And now let us focus on the fact that, you know, if you've got a vector like A, and so if this is A, and A is composed of 2 components, right? One is the horizontal component and one is the vertical component. And so let's say A is, for example, 4 and let's call that 2. And let me, for example, make a second vector B. Let me start even easier. So let's just say B is like that. And so B, imagine B is like that, and that's 1 and 2. So from your earlier kind of work, you know that to work out A plus B, you know that you draw A like this. And then you draw B afterwards from the tip. Something along those lines. And then this would represent your A plus B. And that was your graphical method. And that's all perfectly fine. That is completely valid. But let's just think about it algebraically now. So algebraically, you recognize that A is made up of 4 units here and 2 units there, right? And in my example here, B is made up of 1 unit there and 2 units there, right? And remembering that these are base unit vectors, so therefore they're at right angles to each other. So if you take a look at this, how sort of far across to the right is that?
5.
Right. Kind of you've gone, you know, if you just look left, right, you've kind of gone 4 across and then you went 1 more across, right? And how far up is that?
4.
So basically we can just say that your A plus B is 5, 4. And in other words, if A is 4, 2, and B is 1, 2, then A plus B algebraically is, if you like, 4 plus 1 and 2 plus 2, which is 5, 4.
Wow, very cool.
In other words, if you actually have the numbers and not just focusing on the concepts, but now if you actually have the algebraic numbers and you already have them in their separate components, you can just add the components separately. Does that make sense?
Yeah, so like Pythagoras to find A plus B.
Not Pythagoras. It's not Pythagoras, really.
Mm.
There's no Pythagoras involved here.
Then how do you find A plus B?
We would use Pythagoras to find out the length of A plus B, but,
oh, yeah, that's what I meant.
but
Yeah.
there's no Pythagoras so far.
Yeah.
So therefore, in general, if A is equal to A1, A2, and B is equal to B1, B2, then A plus B would equal A1 plus B1 and A2 plus B2.
Okay, this is fairly straightforward. Nice.
Yeah, a lot of this is, as we said, it's just really not really that hard. It should be quite straightforward, hopefully. It is just a lot of technical definitions that, you guys need to make sure that I need to make sure you guys know, but it's really kind of, this topic is mostly more sort of talking about what things mean, but should be fairly straightforward for the most part. Yeah. Now, note, therefore, negative A would just be negative A1 and negative A2. And therefore, similarly, if you had A minus B, then that would become, well, A1 minus B1 and A2 minus B2, because you're talking about A plus negative B.
Yeah, okay, makes sense.
And similarly, if you had K times A, where K is not a vector, remember, this is quite important here, because vector times vector is a whole different issue, but this is not a vector. It's a scalar. In other words, a number. Then we just multiply the number in. All right.
Cool, makes sense.
Good. All right, so that should be pretty easy then. Yeah. All right. So then, just quickly making sure that you get it. It should be pretty easy, but Janelle, what will be the answer to that?
Oh, is that adding?
No, when you put a 3 in front like that, it's multiplying.
Oh, then it's 3, 6.
Yeah. So let's say Tiffany?
1 and 5. Is there like a specific way to say it, or do I just say like 1 and 5?
For the moment, let's just go with 1, 5. That's fine. All right.
Okay.
And then if we have Paris?
Why is my one so hard?
It's not hard.
Okay, 3.5. 1.
Okay. All right. So what if we had this? Any volunteers? We can work it out step by step. You don't have to tell me directly the answer. So
2 and minus 2 minus 6 and 12. Wait, no, 6 and 12.
So you could either have it as plus minus 6 and minus 12, or minus 6 and 12. Either is fine. Just depends on whether you treat it as 3 times that or negative 3 times that, right? That's up to you. So if we treat it as 3 times this, then that would be 6 and 12, but the negative would stay outside. Yeah. And then, so the answer to that is?
-4. -14.
All right. Okay. Is everyone happy with that?
Yes.
All right. Then I guess we'll do one last thing, which sort of ties in with what we said earlier. So now we're trying to sort of bring in points and vectors together. Remember, points are points and vectors are vectors. You don't want to get the two mixed up. But, you know, if we have point A, as we have repeatedly said, that gives us position vector A from O to A. If you have point B, and in my typical example, I have point B somewhere here. The black dots are points, but, you know, the arrows are the vectors, and that would represent OB. And, you know, I could start putting in something. So, you know, this would be point A1, A2. This would be point B1, B2. And you can hopefully see, based on what we said before, and we'll just quickly draw it in quickly again. I'll rub it out very shortly, but just reiterating an earlier point, that would be vector A drawn from B. And so therefore you'll get to a new point. Let's call that new point, you know, C, right? So this is the point C, which will be at the point A1 plus B1, A2 plus B2. And your position vector C so your position vector C would be A plus B. And hopefully you can see how that ties in both graphically and algebraically. And we can also, of course, have gone from A plus B from this end. And assuming you have drawn everything perfectly, you know, the green lines are meant to be perfectly equal in length and parallel. And the blue lines and the green lines are both meant to be equal to each other and parallel to each other, which means you get a parallelogram, and this C here will be your diagonal. And, you know, hopefully if you think about it sort of algebraically, you can see that this is A1 across and then B1 across, giving you A1 plus B1. If you think about A2 up and B2 up, giving you A2 plus B2. Think of it like sort of your X and Y coordinates. Or you can think of it as B2 across, B1 across, then A1 across, giving you again A1 plus B1, or B2 up, then A2 up, giving you A2 plus B2. Regardless of which way you get to the same point, which in my case I've labeled it C, which is not A and which is not B, and is a new point, giving you this thing here. Now, we'll stress again that this thing is vector A, so this is also vector A, even though it's not drawn from O and has nothing to do with point A, so to speak, because it's the same length and the same direction. And if I had done, you know, something like here, or here, or here, or here, assuming they're the same length and direction, they would all be vector A's. All right. So you guys are all happy that C is the length of this diagonal, right?
Yes.
All right. And that's all repeating what we said earlier. But now I want you to consider this. Let's go from A to B. So this red arrow is a vector, right?
Yes.
And it's a red arrow from point A, so originating from A and terminating at B, right? So it must be vector AB. I mean, there's no question about that, right?
Mm-hmm.
It's a vector from point A to point B, or originating at point A and terminating at point B, which means it's vector AB. That, by definition, is vector AB using this notation. Now, how could we represent vector AB? Is there a way that we are able to represent vector AB?
Would it be A minus B?
Well, that's something we could try and think about. So Tiffany has a suggestion of perhaps it's A minus B. So let's put that as option 1. Does anyone have any other suggestions, or does everyone agree that it's A minus B? Or like, you know, what does everyone think? Janelle, what do you think?
Wait, no, that's not right. Wait.
So just, you know, we'll think about it and then we'll talk about it. So right now, Tiffany has suggested A minus B. Janelle, do you have any suggestions?
I don't know.
Harris, do you have any suggestions?
Isn't it still the same, but one of them is negative?
What do you mean by isn't it the same, but one of them is negative? What do you mean?
Oh, I think like, isn't it still A plus B, but
So-
then A or B is negative? Oh,
No,
wow.
that doesn't make sense, because then it would be like that.
Wait,
and then you try and go backwards.
So in other words, you're saying, Paris, that it's negative A plus B or negative B plus A. Is that what you're trying to say?
Oh, yeah.
No, that doesn't make sense.
Okay, so we'll demonstrate. We'll you know, really, A minus B is this scenario, right? So that's this part, right? So A minus B is here, and then you've got this other B minus A. And so kind of you guys are sort of gravitating towards these two sort of choices. So let's figure out what A minus B looks like, and let's figure out what B minus A looks like, all right? So we've got our vectors drawn out for us, and we know how to do this, so let's do it. So don't worry about, you know, what AB is right now. Let's just work out exactly what A minus B looks like and what, you know, B minus A looks like. So option 1 in blue, hopefully. So you've got A. That looks something like that. And then you want to minus B. Well, B kind of went up, right? So B would have, you know, B would have looked something like this. That's B-ish. But we want minus B, so we kind of want to go this way. You want to add them together, giving you this one. And we're saying that's A minus B, yeah? Now, does A minus B look like AB?
No.
Why not?
Wait, yeah? It does.
Well, AB is this, right?
But it's the, yeah, it's a different,
And A minus B is this, right?
yeah.
So are they the same?
No.
No.
I have an idea, but I'm not sure if it's right.
So let's take a look at the other one. So now let's look at B minus A. So B looks something like this. Let me draw it further to the right because of what will happen. So this is an approximately what B looks like. And then A would have looked something like this. But because we want minus A, you kind of want to go the other way. So you want to do it like this. And therefore, this here would be B minus A. Does this look like your AB?
Yes.
Yeah. So in other words, vector AB from point A to point B will always equal B minus A, where B in this case represents the position vector of B and A represents the position vector of A. In other words, it's one vector minus the other, one position vector minus the other position vector. Now, lots of students get them the wrong way around, which means if you do get them the wrong way around, then I guess, draw it out and figure out which way it is, because they'll both be A, B kind of thing, but one of them will be the right way around and one will be the wrong way around. So if you ever get confused, draw it out and figure it out. But another
Wait, I don't get it. What is the right way around? What is the wrong way around?
Well, AB goes from A to B, so it's this direction, right?
Yeah.
So that's this one.
Oh.
This one is like, literally the same thing, but it's pointing that way.
Oh, yeah. Oh, okay, yeah.
So, if you're ever confused about which way around these go, then just draw it out and figure it out. I can, tell you to memorize it's B minus A, and I'll show you, tell you how I might think about it. But, if for whatever reason you're not 100% sure which way around they go, then just spend your 30 seconds or whatever and figure out which way it goes, because you don't want to get this wrong. So AB is going to be B minus A. And basically, it's always your final position minus your initial position. So basically, think of it like, how do I get from A to B? Well, you got to backtrack. You got to go from B and, figure out where take away how you got to where you started from, right? Imagine you took a long, you went a long kind of distance and it was a sort of nightmare to get to A, and then you went from A to B. Well, think of it as, how do we get to B, but forget all the bits that it took us to get to A, all right?
All right.
Tell me when you're done with this page.
I'm done.
Done.
Janelle?
Yeah.
All right. So therefore, to reiterate, AB is the vector from A to B, which means it is going to be equal to B minus A, or in other words, the position vector of B minus the position vector of A. And you can't get this the wrong way around. You get it the wrong way around, you won't get AB, you'll get BA. Now, one way to think about which way to sort of subtract, I suppose, is I think we all agree that OA is the vector from, O to A, right? Which we know we consider this vector A, right? Like we all agree this from earlier, right?
Yes.
But you can think of O itself is a point, right? So, if you're going from O to A, I guess you can think about it as something vector 1 minus vector 2. And one of these is A and one of them is 0, right? And so if you ever get confused, maybe trying to think about it from the position vector point of view. So if you're OA, you're going from vector from O0 to A. So that must be equal ultimately to A. That is the right answer. So it's A minus 0, which means this represents the final position where you're at. So you're ending minus the starting. Because if you do it the wrong way around, and you do it as 0 minus A, then you'll get negative A, which clearly is not right, because OA has to be A, not negative A.
Yes, makes sense.
Good. So if you have any trouble with that, just find some way to sort of figure it out. Either draw it out, think about the sort of position vector or anything like that, but make sure you do not get it confused. You get the order wrong, your answer will be wrong. Okay. And so the short version is, vector from A to B is vector B minus vector A. And that's really all you need to sort of make sure you hammer it. Okay. Is everyone happy with that?
Yes.
Okay. Well,